Hello, good morning everyone. Welcome to One Concept Per Day portal. For the past few days, I was not able to put across any videos. Reason was I was quite busy with the school work and other official work. Anyway, let us begin once again. Even this week also, I think I'll be able to put only some 2 to 3 videos. And anyway, so let me see how much I can put it across. Okay, so to begin with this week, so this particular video is focused more on specific heat capacity. And as you know, most of the questions in IB physics, that is especially related to this topic, it would not be purely specific heat capacity, but it will be a concept that is related to both specific heat and as well as electricity. So I've taken up some specific unique problems, okay, which are related to both the concepts. Somewhere I felt, okay, only a pure concept will not be applicable, and we need to have concepts which are interlinked also. Okay, only then you will be able to get adjusted to write the exams appropriately. Okay, let us begin with this. Okay, with the first question, so define specific heat capacity. So what is that you should write? You should write specific heat capacity. Specific heat capacity is the amount of heat required to raise the temperature of an object by 1 degree centigrade per unit mass. This is a definition of the specific heat capacity. So if you want to write it as an equation, you can write Q is equal to mc delta T, or in other words, C, which is the specific heat is equal to Q divided by m delta T. If you do not remember this definition here, you can just look into this equation and then write down the definition of specific heat. As you see here, C is equal to amount of energy required to raise the temperature of 1 degree centigrade per unit mass. So everything is coming over here. Okay, let us move on to the next one. Explain what happens to the molecules of an ideal gas when the temperature of the gas is increased at constant volume. When you increase at constant volume, which means what? Your delta V is 0. Change in volume is 0 when you say constant volume. Okay. What happens to the temperature of the gas? To the molecules of an ideal gas. What happens to the molecules of an ideal gas? So how to be write? So the molecules of an ideal gas, what happens? You will describe it in terms of energy. Okay, so when you say V is equal to constant, delta V equal to 0, it means we have a piston and the piston is being tightly held over here. Now as you increase the temperature of the gas, okay, at constant volume, what will happen to this volume, to these molecules? Okay, so then the internal energy will increase. Internal energy will increase. Internal energy increases. Why internal energy increases? Because you see, temperature of the gas is increased. So temperature is directly proportional to internal energy, and as a result of it, the internal energy should increase. First thing. Is there any work done? Work is not being done. Okay. Work done is 0. Work done is 0. What else can we say? We can also say temperature increases. Yeah, so that's it. Internal energy is equal to is increases, work done is equal to 0. And you can say what kind of process is this for us? It's constant volume. You can say this is isochoric process. Isochoric process. Okay, let us move on to the next one. Apply the first law of thermodynamics to show that if the temperature of the gas is raised at constant temperature, at constant pressure, not constant pressure, the specific heat capacity of the gas is different from that raised at the constant volume. It means what he says, specific heat is different at constant pressure, specific heat is different at constant volume for a given gas. Which means there are two different types of specific heats, one at constant pressure, the other one at constant volume. And show that there exists two different specific heats. Now, to argue with this law, first let us define what is specific heat. What is specific heat here? We already said specific heat is the amount of heat required. So let me write down specific heat. Specific heat is amount of heat required. Amount of heat required. That's what is the amount of heat required. So when you say, I'm not writing the full statement, I'm just writing only a part of this. Now when you say so much, now how do you write mathematically the amount of heat required? You will write Q is the amount of heat required. So what does this Q do? This Q, when you supply some amount of energy, it either increases the internal energy or it increases the work done. What is this statement? This statement is nothing but first law of thermodynamics, right? The first law of thermodynamics tells you the amount of energy that you have supplied to a system goes in increasing the internal energy, and as well as some amount of work is also being done. Okay, so this is your first law of thermodynamics, which is in accordance with your conservation of energy. How much of energy you have supplied, this is what actually it does. Now, when you say at constant pressure, when delta P is equal to 0, okay, then this Q, I can now write Q at P. Q at P, okay, and then let us say it is useful in increasing the temperature of the gas by a delta T, Okay, when delta P is equal to 0, volume can increase. Okay, then you can say this M multiplied by delta T, okay, and this by C, I can write this as Cp is equal to so much. Okay, so in other words, I can now write Cp is equal to Qp divided by M delta T. The amount of heat energy supplied is equal to mass of the gas multiplied by rise in temperature multiplied by the specific heat at constant pressure. I mentioned this. Okay, now next is we have when delta V is equal to 0. Why delta V equal to 0? See, look at this here at constant volume. When delta V equal to 0, what happens to this equation? In this equation, now Q, let me say QV is equal to only delta U, right? This P delta V doesn't come over here. So only delta U. When you say delta U, that means it only raises the temperature. Okay, let me call this temperature delta 1. So as a result of it, now once again, I can now write this as equal to mass times delta T2 into Cv. Now do you think the temperature rise will be the same? Temperature rise will not be the same. Here the temperature rise will be larger. Here the temperature rise will be lesser over here, right? Because you know some amount of energy is taken here also. I'll just give you a numerical example if you want. Let us say, for example, you are supplying something like around 500 joules over here. Okay, when you supply 500 joules, let me assume 400 joules goes in internal energy rise and 100 joules goes in increase in the what you call the work done. Okay, the volume also increases over here. Now this is what happens. So this 400 joules is responsible for the rise in temperature here. Okay, now in this case what happens, all the 500 joules comes over here. Okay, as a result of it, this delta T would be much larger, right? So delta T1 and delta T2 are not equal. Okay, so therefore I can now say from these examples, I can now say that delta T1 would be less than delta T2, right? Temperature rise here would be lesser than the temperature rise here. So which means now here what I do is in a similar way like how I defined over here, I'll write Cv is equal to Qv divided by M delta T. Okay, so therefore Qp and Qv are same. I am supplying the same amount of heat energy. Q is not changing. M is also not changing. So what will happen? Cp and Cv are now indirectly or inversely proportional to the change in temperature. So from here what I can write? I can write Cp is greater than Cv. See, we have done two things over here. First is I have proved that Cp and Cv, there are two specific cases available. Second thing what I have done is I have showed that Cp is greater than Cv. Okay, in advanced thermodynamics, you will also be able to learn that Cp minus Cv is equal to something like R, which we call it as a Victor-Mayer equation. You don't have it in your current syllabus, but this is what you will be learning in your higher thermodynamics. Okay, with this we come to an end to the first video, and we will see the next video about some more examples of using the specific heat and relating it to temperature, resistance, voltage, current, power, all this, okay, which is related to this. Thank you.